We talked about using the loop functions, but in fact, we need to think about efficiency, computing efficiency. To improve computing efficiency, when it's possible, we need to do vectorization. So here is a for loop example where t loops from 0 to 50 with a step size of 0.02. So inside this for loop body, first line is I equals I plus 1. I will be increased by 1. And yi, which is the ith element in a vector y, will be equal to cosine t. So for each small t changes, we have a new y element added to the vector y. And in fact, this will return a y vector of cosine t, right? Cosine t vector. So we can replace this for loop with the following. First, we generate t as a vector, 0 to 50 with a step size of 0.02. And then we directly do a cosine operation on the t vector, and we can get the y vector easily. So it's pretty straightforward, and it's called vectorization. And whenever possible, vectorization is recommended because it's a way to improve computing efficiency. Another way to improve efficiency is memory pre-allocation. So a bad example is on the left side, where we again have this t vector generated from 0 to 5 with a step size of 0.01. And then we have I as our variable for the for loop. If ti bigger than 1, we give yi, which is the ith element in the y vector, to be 1 over ti, else yi equals 1. So as I increases while running the for loop, the y elements will, y size will increase again and again and again. But we didn't predefine a space for this y vector because we don't know how long this y vector will be. So we just add elements to the y vector dynamically. And this usually will cause memory allocation workload, which is not necessary if we use the right side solution, which is instead of generating just the t vector, we also generate a y vector with all ones. Y vector is ones of size of t. So we pre-allocate a space for this y vector, and then inside the for loop, we fill each element of the y vector with the calculated value. So this is a way to pre-allocate memory for a variable, and it will avoid fragmentation of the memory. So next, let's talk about nested for loops. Based on the name, we know there is a nest somewhere, right? If you look at the example code here, we have the outer for loop for j equals 2 to n, and the end, we have an end line to end this for loop. And inside this for loop structure, we have another for loop, which is for I equals 1 to j minus 1, and some execution there with commands, and also again, it will end with an end line. So if we look into the steps of carrying out the nested for loops, in loop 1, we have j equals to 2 and I equals to 1. So in the first loop, we will generate two values. The first value is aij, which is a12. After calculation, we get 0.5. Similarly, we get aj. I already runs through its range. We will increase j, the outer for loop, to be 3, so that we can execute A13 and A31. Now in loop 3, since I just looped through 1, it still has a value j minus 1 equals to 2 to be looped through. We now have I equals to 2 and j equals to 3. So in this loop 3, we calculate A23 and A32. Now we finished the inner for loop. We go to loop 4, which is to give the j value to the incremental, which is 4. So now I goes back to value 1, the inner nest. And now we in loop 4 we execute A14 and A41. So eventually we will have all 4 by 4, which is 16 loops executed. Again, pay attention to the order. The inner loop has higher priority in execution. So you need to execute all I variables first before you increment the j variable, which is the outer for loop. So some examples of the while loops. Again, revisit the while loop structure. While condition, if the condition meets, then the statements will be executed until the condition does not meet anymore. Then we can end the while loop. An example is like the following: x equals to 8, x is given to 8, and while x larger than 0, we will do x equals x minus 3, which is to deduct 3 out of x and display this x. And we can see that once x was subtracted by 3 times, it will be minus 1. And by that time, this while loop will end. And there's another while loop, which keeps the loop going on and on, which is called while 1. And in this case, usually we will set an if condition inside the body of the while loop and use the command break to break out of the while loop. An example is while 1, that means always run this while. If x smaller than 0, break, end. X equals x minus 5. So in the previous example where x was initially given to 8, in the first loop of this while loop, x is 8, so it won't break. It goes to the next line, which is x equals x minus 1, which gives us x equals to 3, right? So then it goes back to the while loop again and see if x is smaller than 0. It's 3, it's not smaller than 0. So the break won't happen, and x will be x minus 5, which is this time negative 2. And this loop ends, and we go to the next loop. Now we see if x is negative 2, smaller than 0. Now we break. So the next line, x equals x minus 5, will never execute again because we already break out of this while loop. Okay, this is the end of lecture 2. Please write down any questions you might have and bring them to the lab exercise session so that we can discuss together.